And welcome back as we continue our cosmic journey. We, of course, previously talked about the death knell for low mass stars. But when we start looking at that of our much more massive stars, we actually find that they tend to have a much more explosive finish. And a lot of this happens because we have the nuclear fusion of heavy elements. After the helium in a massive star's core is exhausted, the evolution of a massive star takes a very significant different course from that what we saw in the lower mass stars. This is because the weight of the outer layers is actually sufficient enough to force the carbon core to contract until it becomes hot enough for it to fuse carbon to oxygen, neon, and magnesium. Now this cycle of contraction, heating, and the ignition of another nuclear fuel will actually repeat several more times. After each of the possible nuclear fuels is exhausted, the core contracts again until it reaches a new temperature hot enough to fuse a still heavier nuclei. Now the products of carbon fusion can further be converted into silicon, sulfur, calcium, and even argon. Now these elements, when heated to a still higher temperature, can eventually combine to produce iron. Now massive stars go through these stages very, very quickly. Just how they formed very, very quickly, they're also going to burn toward their end of life extremely fast. In supermassive stars, some fusion stages towards the end can take anywhere from a few months to even just a few days for it to move through these cycles. This is a very far cry from the millions of years they spend in the main sequence stage. And also a very big contrast to what we saw for our lower mass stars, which take a very, very long time, we're talking billions of years, for things to progress. Now, when we actually look at our massive stars, in this stage of evolution, we're actually going to see that the massive star represents an onion with an iron core. As we can see here represented in this image, we have different layers of silicon and sulfur, oxygen, neon, carbon mixed with oxygen, some helium, and hydrogen. As we get further and further from the center, we of course find the shells of decreasing temperatures in which the nuclear reactions involved have progressively lower mass. So silicon and sulfur, like we saw here, oxygen, neon, carbon, helium, and finally hydrogen. Hydrogen being the outermost shell because it is going to have the lightest amount here. These things are much more dense as we move toward the center. But there is, though, a limit to how long this process of building up elements by fusion can actually go on. The fusion of silicon into iron actually turns out to be one of the last steps in the sequence of non-explosive element production. Because up to this point, each fusion reaction has actually produced some energy because the nucleus of each fusion product has been a bit more stable than the nuclei that formed it. And night nuclei, such as things like helium, give up some of their binding energy in the process of fusing into more tightly bound heavier nuclei such as carbon or oxygen. It is this released energy that maintains the outward pressure in the core so the star does not actually collapse. But of all the nuclei we know, iron is the most tightly bound and thus is one of the most stable elements out there. And while it may seem that all smaller nuclei want to be like iron, going towards stability, they're willing to pay in the form of producing energy to move toward that goal. But iron is a little different in that it requires energy, in other words, it must absorb it to really change its stable nuclear structure. This is the exact opposite of what's been happening in each of the nuclear reactions up to this point. So instead of providing energy to balance the inward pull of gravity, any nuclear reactions involving iron would then remove some energy from the core of the star. And because we're removing energy, the star is now unable to generate energy and so is now actually going to face a catastrophe. So the first thing that's going to happen is a collapse into a ball of neutrons. When nuclear reactions stop, the core of a massive star is supported, of course, by degenerate electrons, just as what we saw within the core of a white dwarf. For stars that begin their evolution with masses that are at least 10 times the mass of our sun, this core is likely made mainly of iron. For stars with initial masses that are in the range of 8 to 10 solar masses, the core is likely made of oxygen, neon, and magnesium because the star actually never got hot enough to form those heavier elements such as iron. Now, the exact composition of the cores of stars in this mass range is very difficult to determine because of the complex physical characteristics involved with those cores, particularly at the very high densities and the temperatures that are involved. Now, while no energy is being generated within the white dwarf core of the star, there of course is still fusion occurring in the shells that surround the core. As the shells finish their fusion reactions and stop producing energy, the ashes of the last reaction fall onto the white dwarf core and then increase its mass. Now, higher mass means a smaller core, as we saw before. The more mass you feed into a white dwarf, the more it's going to compress. Now, the core can contract even when we have a degenerate gas, because remember, it is still a lot of empty space in between. It doesn't like to collapse, but there's still empty space where it can try to force things together. Now, the electrons at first resist being crowded so close together, so of course the core is only going to shrink a tiny amount, as we saw with the white dwarfs. Ultimately, though, if you have an iron core, it's going to reach a match so large that even degenerate electrons can no longer support it. And when the density reaches about 400 billion times the density of water, some electrons are actually squeezed into the atomic nuclei itself, where they actually combine with protons to form neutrons and neutrinos. Now, some of the electrons are gone because, of course, they combined out, and the core can no longer resist the crushing mass of the star's overlying layers. They don't have that degenerate electron to help push back. So the core begins to shrink rapidly, and more electrons are now being pushed into the atomic nuclei, which ultimately becomes so saturated with neutrons that they can't hold on to them. They are very unstable. At this point, the neutrons actually then end up being squeezed out of the nuclei and actually can exert a new force. As is true for electrons, it turns out that the neutrons strongly resist being in the same place and moving in the same way. The force that can be exerted, though, by such a degenerate neutron is much, much greater than that is produced by degenerate electrons, so unless the core is too massive, they can ultimately stop the collapse, and so kind of enter into a new stasis. The collapsing core can then reach a stable state as a crushed ball made mainly of neutrons, which astronomers refer to as a neutron star. We don't have an exact number for the maximum mass of a neutron star, but our calculations roughly tell us that the upper mass limit of a body made of neutrons might only be about 3 solar masses, so not too much larger. Now, if the mass of the core were greater than this, then even neutron degeneracy would not be able to stop the core from collapsing further. This dying star must then end up as something even more compressed, which until recently was only be one possible type object, a black hole. Now, this is because no force was believed to exist that could stop a collapse beyond the neutron star stage. And so what's going to happen then if we do trigger a greater collapse? Well, this is when we're going to collapse and have that explosion that we promised you in the beginning. Because when the collapse of a high-mass star is stopped by degenerate neutrons, the core is saved from further destruction, but it turns out that the rest of the star is literally blown apart. The collapse that takes place when electrons are absorbed into the nuclei is very rapid. In less than a second, a core with a mass of about 1 solar mass, which originally was approximately the size of Earth, collapses to a diameter of less than 20 kilometers, which is very, very compacted. And the speed at which material falls inward reaches actually about 1/4 the speed of light. And the collapse halts only when the density of the core exceeds the density of the atomic nucleus. So the neutron degenerate core strongly resists further compression and abruptly halts the collapse. Now, this shock of the sudden jolt from the collapsing and then stopping actually initiates a shock wave that starts to propagate outward. However, this shock alone is not enough to create a stellar explosion. Instead, the energy produced by the outflowing matter is quickly absorbed by atomic nuclei in the dense overlying layers of the gas, where it breaks up the nuclei into then individual neutrons and protons. Now, each time an electron and proton in the star's core merge to make a neutron, it's going to release a neutrino. Now, of course, these ghostly subatomic particles are going to carry away some of that nuclear energy. Now, it is their presence that actually launches the final disastrous explosion of the star. The total energy contained in neutrinos in the initial second of the star's explosion, the power that is carried out by them, is actually greater than the power put out by all stars in over 1 billion galaxies. It's that much of an energy release. So while neutrinos ordinarily do not interact very much with ordinary matter because they just pass through the open spaces, matter near the center of a collapsing star is so dense that the neutrinos do interact with it to some degree. They actually then deposit some of this energy into the layers of the star just outside the core. And this huge sudden input of energy reverses the windfall of these layers and then drives them explosively outward. And what happens is that we find most of the mass of the star is then ejected outward into space. And so this is, of course, going to give us to the supernova, which, of course, can give and take away different things about how we view our solar and stellar skies. Now, after a supernova explosion, the life of a massive star comes to an end. But the death of each massive star is still an important event in the history of its galaxy, because what happens is the elements that are built up by fusion during a star's life are now recycled into space by the explosion, making them available to enrich the gas and dust that form new stars and planets, releasing hydrogen, releasing helium, oxygen, etc. And because these heavier elements ejected by supernovae are critical for the formation of planets and the origin of life, it's really fair to say that without the mass loss from supernovae and planetary nebulae, we would not exist because those heavier elements would not be possible. Now, the supernova explosion, of course, produced a flood of energetic neutrons that barrel through the expanding material. Now, these neutrons can, of course, be absorbed by iron and other nuclei where they can actually be transformed into protons. Thus, they are actually going to build up elements that are much more massive than iron, including things such as gold, silver, and even uranium. Now, supernovae and the explosive mergers of neutron stars are the only candidates that we know of that have places where such heavier atoms can actually be made. Now, supernovae are also thought to be the source of many of the high-energy cosmic ray particles that we have talked about previously. These, of course, are trapped by the magnetic field of the galaxy, and the particles from the exploded stars actually continue to circulate around the vast spiral of the Milky Way. Supernovae may have actually played a part in the development of new generation of stars, planets, and life due to mutations from the cosmic ray energy. Now, supernovae, while necessary to life, of course, can also carry a bit of a misfortune. So let's just say, suppose the life form has the misfortune of developing around a star that happens to lie near a massive star destined to become a supernova. Such life forms may find themselves snuffed out when the harsh radiation and high energy particles from a neighboring star's explosion reach their world. Now, if life can develop on many planets around long-lived stars, then the suitability of that life's own star and planet may not be all that matters for its long-term evolution and survival. In fact, life may well have formed around a few pleasantly stable stars, only be wiped out because a massive nearby star suddenly went supernova. In fact, if we look at our own planet, we might wonder how has our own planet survived in the past from maybe nearby supernova explosions. Now, currently, there are no supernova that are near enough to our planet that pose a threat to us, but that doesn't mean that it isn't something that we can look at and really kind of ponder what kind of possibility could this have if we were to get some kind of supernova shower. And lastly, let's just take a quick look at the ultimate fate of these stars and substellar objects with different masses. So when we start looking at these different things here, for example, when we look at the initial mass of something that is, 0.01 the mass of our sun, we can see that it's going to just simply end up as a planet. As we start moving up in scale, we move to a brown dwarf, then we get a white dwarf that's made mostly helium. We get up to 0.25 to 8. We get a white dwarf that's mostly carbon and oxygen. Again, this is probably where our sun is probably going to end up. We have 8 to 10 times, again, a white dwarf now made of oxygen, neon, and magnesium. Once we get to 10 to 40, though, we get a supernova explosion that's going to leave behind a neutron star. And if we manage to get all the way up to greater than 40 times our sun, we'll actually have a black hole that is left behind instead of a neutron star.